Good day, mate. This is Algebra 2, Chapter 2, Section 6, Special Functions. And I'm kind of in the dark here. I wanted the graphs to really stand out, and that they seem to look a little better, at least in the classroom, when the lights are out. You can let me know later if it's too dark, and in the next lesson I won't do that. But here we go, special functions. In particular, today we're talking about piecewise functions. And so a lot of times this can be really confusing for some people, but I'm going to try to just make it as straightforward as possible so that you don't need to flip out or anything like that. But a piecewise function is just that. It's a function that is composed of two pieces. So we understand that x minus 2, if I just had y equals x minus 2, that would be a function in and of itself. Also, y equals x plus 3 would also be a function in and of itself. So what we're doing is we're taking two functions and we're going to combine them into one function. Now you will recall the vertical line test. So I just kind of want to show you some things that we're not talking about here. For example, let's just say that I want to graph y equals x minus 2. This is a very basic y equals mx plus b equation, and if you remember, with y equals mx plus b, negative 2 is the y-intercept, so I come down to negative 2 on the y-axis, and that's my y-intercept. And then my slope is the number in front of x, so in this case 1. So I go up 1, over 1, and then I put my second dot. I connect the two dots together, and I get a line that looks like this. So far, so good. That's the function y equals x minus 2. In a similar fashion, we can graph y equals x plus 3, and in that case, your y-intercept is 3. So I would go 1, 2, 3, put my dot there, and then my slope again is 1, so I would go up 1 over 1, up 1 over 1, and then I'm going to connect these two together. One thing you might be noticing right now is that these two lines are very parallel. They have the same slope, so that would make sense. And as you look at them, they shouldn't be crossing. And for the most part, they're not. My graph's a little off over here, but there you go. Now, right now, a couple of red flags should be flaring up. This function fails to pass the vertical line test pretty much everywhere. You are not a function if you can draw a vertical line and you can see that my ruler is acting as a vertical line and it's crossing in two spots. So this is the epitome of what is not a function. So one thing that you might be noticing right now is that to the right of the piecewise function are these conditions. It says if x is less than negative 1. It says if x is greater than or equal to negative 1. So how does that apply to my function? We don't actually want to graph all of the function. This is basically telling us when to graph it. And it's all based on the x-axis. And it wants me to graph the top function, the x minus 2, whenever x is less than negative 1. So on the x-axis, I have to find where negative 1 is. And so right about here is negative 1. So I'm going to draw a dashed line just to make it more visual for everybody. Let's see here. We're going to graph a dashed line right here. Now remember, this line is not actually part of the graph. It's a vertical line. It's not actually part of the graph, but it tells me that for the blue line, which is the one we graphed first, the x minus 2, for this function, they don't want me to graph it only for x less than negative 1. So which side of the red line is where x's are smaller than negative 1? That would be to the left. So that means that I need to erase the other portion of it. So this piece right here needs to be erased all the way up until where it touches that line. Okay? Which of course means that I'm going to have to fill in some things that I got rid of. So I will do that. We want to fill this back in. We erase this. We have to put it back in. Put my x-axis back in. Put my y-axis back in. There was negative 2 right about there. Also, you'll notice that it's a less than, not a greater than. So what we're going to do is right here we're going to put an open dot. Okay? So we are only graphing, oops, the open dot here. All right there is where we have an open dot because it doesn't include -1. All right, but again, we've kind of cleared up the area on this side. The vertical line test will pass on this side, but now it doesn't pass on this side. But lo and behold, we also have a condition for x plus 3. It tells us to only graph this function when x is larger than or equal to -1. Okay, so that's telling us is that, here's again that x -1 right here. It tells us that it wants us to keep the part that is greater than or equal to -1. So we want to keep the right-hand side, but this time we're going to erase the left-hand side. So we're going to erase this piece ever so carefully there. And then we get back our x-axis. Okay, and this time it's telling us that it's x equal to -1 is included, so we're going to put a big black dot right there. Okay, and now when you use the vertical line test, and again if I use my ruler, if I do it on the left of the red line, then it passes the vertical line test. If I do it on the vertical line, you can see that this counts, this one does not because it's open, so it passes the vertical line test. And if I draw it on the right of the red line, it also passes. So now this function is totally okay. It totally passes the vertical line test, and that's the graph. You basically take two pieces, two separate linear functions, and you put those two pieces together. Now the second part of this problem is asking us to find the domain and range. Now, since all of the x values were accounted for, we know that when we're smaller than -1, we have x values that are valid here. When x is equal to -1, it's right there. And when x is greater than -1, we have the pink line that represents that. So for our domain, we get all reals. Everything counts. And then for our range, where are our possible y values? You can see that our y values are starting right about here at -3 and then go down. From here down, you have y values. But in between here and here, there are no y values. So then we have the y value starting at 2 and then going onward. So we're going to write that for our range of this particular function, it's going to be 2 parts to it. All right, so over here for range, you can do this in interval notation or you can make them 2 separate ones. But either you have y values less than, and not equal to, because again, it doesn't equal to this value here, less than -3. Okay, so for the range, we have y values less than -3, or your y values are greater than or equal to what appears to be +2. 1, 2. All right, so those are your y values. Again, just be clear that there's no y values in between here. There's only y values here down and here up. So this piece in here is like a little gap. So there is how you do example 1. And now hopefully you will be able to try this one on your own. Same idea, you're graphing a piecewise function. This time the condition is less than 0 and greater than or equal to 0. And then you'll find domain and range. All right. So the other thing that you can do with the piecewise function is go backwards. Sometimes they can give you a graph, and then your job is to write the equation of the function. Okay. So we know that we have 3 pieces here. I hope you're not getting too frantic just yet. We'll just do a piece at a time. And what you can tell probably right now is that there are going to be 3 pieces. We can see that there's this piece here, this piece there, and that piece there. So the first thing we need to do is find the equation of the line. And so that's going to be based on y equals mx plus b. So hopefully that's still fresh in your minds. For this piece right here, it looks like, and again, you can find these examples on page, let's see here, 102 of your book. So I definitely drew it on my board, but sometimes when I draw them on the board, they're not as exact as the ones in the book. But I tried really hard to be really accurate here. So in this case, what you can see is that It appears to have 1, 2, 3, the y-intercept at 3. So if you use y equals mx plus b, it appears in this case that my y-intercept is positive 3. And then if we use the slope, we can see that from here, you can go up 2 units and to the right 1 unit, and then you're at the next point. So that means that my slope is 2. So just using that information, I know that the first piece is y equals 2x plus 3. That's my first piece. And then in a similar fashion, we try to do that with this problem. What you're going to see with this problem is that you can't see where it crosses the y-axis, but you can kind of guesstimate that since this is going down 1 over 1, that if I go up 1 and left 1, we would probably be right here, and this point is 2. So even though it's not fully connected, it looks like this line is basically going to have a y-intercept at 2. So again, using our little formula, y equals, our y-intercept is going to be plus 2. And the slope is down 1 to the right 1, down 1, right 1. So it's going to be negative 1. So then our second piece is going to be negative x plus 2. And then we have one more piece, and that piece is right here. And this one's kind of easy because it actually looks very horizontal. And I don't know if you remember, but I can tell you right now that anytime you have a vertical line, the equation will be x equals some number. But whenever you have a horizontal line, then the equation will be a number. And the number that it equals is where it's crossing on the y-axis. So we can see here that this is 1, 2, 3. So y equals 3 is the equation of this last piece right here. All right, so that's pretty much done. The hard part is done, finding the equations. And now all you have to do is write the conditions. Okay, so for the conditions, you saw how they were in the last example. We're going to put if, and if. Okay, so basically what we're saying is for the first part of the line, this is x equal to 1, it's all based on x. So we're looking here at 1, and that's kind of where this one starts. So I can get my ruler here, which can see this is kind of where, this is 1, 2, 3, 4, 5. This is x equal to 1, and that's kind of where it ends. So we want to start there. So we're going to say that this is going to be the points that are to the left of negative 1 are what we call less than negative 1. So here we're going to say x less than negative 1. We're not going to use an equal to because it's an open dot, so it's not an equal to. The next one is going to be an equal to because it's a closed dot, and it's going to finish at an equal to because it's a closed dot. So this is between 1 and 2. So now we're going to say if x is between 1 and 2. And that's how we write x between 1 and 2. X has to be greater than or equal to 1, but at the same time smaller than or equal to 2. So that's the condition for the middle part. And the last part starts at 2, but doesn't equal to. Again, we have an open dot here. So it starts at the 2, and then it goes on forever, so greater than 2. So x is greater than 2. And that is how you piece together your, and I just noticed that I put here less than negative 1. This should be less than positive 1. My bad. Sorry about that. This is actually a positive 1 over here, not a negative 1. So what we can see is that we have values from negative infinity all the way up to negative 1, including negative 1 right here. And then we have values all the way from negative 1 to 2, totally okay. And then from 2, we have values all the way. So again, our domain, because that's the second, well actually, we don't need domain. It says just write the equation, so we don't have to find the domain. So we're done. You write the equations of the pieces, and then just make sure that you write the correct ranges for where those pieces are taking place. All right, so that's that. And so then you will try this little guy. There's 2 of them here, each having 3 pieces. So again, if these graphs are a little bit unclear, you can look in your textbook on page 102, and you will find the graphs there as well. Okay, so now we're going to move on to another type of piecewise function, and it is called the greatest integer function. And before we go into the example, I kind of just want to introduce this function to you if you haven't seen it before and whatnot. So, first of all, the notation, this funky looking x thing. It's kind of like y equals x, but it has these weird brackets around it. And just so that you know, the way that you draw those is you make a bracket, and then you put a line inside. Make a bracket, put a line inside, and there you go. That's how you make it. Okay? So I want to give you the definition of what the greatest integer function is. This is the greatest integer function, is what we call it. It's a type of step function. The reason why it's called a step function is because when you graph it, it looks like a little ladder with a bunch of little steps. And that's why it's called a step function, but its formal name is greatest integer function. And this symbol means that it's looking for the greatest integer that is less than or equal to x. And that's what causes confusion, because you see the word greatest and less in the same sentence and it kind of throws you off. But let me just explain, okay, why it can't be just one of those two words. 3.25 inside of these brackets means that I am looking for a number that is the greatest integer less than or equal to x. Why can't it just be a greater integer? Lots of integers are greater than 3.25. And again, first of all, 3.25 isn't an integer, but integers that are greater than this are 4, 5, 6, 7, 8, 9, 103, a million, 1,000,005. There's a lot of numbers, integers, that are greater than 3.25. Okay? But what it's asking for is it wants an integer that's actually less than or equal to x. Okay? So if you look for integers that are less than 3.25, again, you have an infinite amount of integers that are less than 3.25. You could say 3 is less than 3.25. 2 is less than 3.25. 1 is less than 3.25. 0 is less than 3.25. Negative 10 is less than 3.25. You can go on forever. So to be specific and so that you only get one answer, it says it wants the biggest number that is also less than or equal to itself. So we want the biggest integer that is less than 3.25. And at that point, the answer is obviously 3. Get my pen back here. 3. 3 is the biggest integer that is less than 3.25. Okay? Because again, 2 is less than 2.5, but 3 is bigger than 2. So now we only get one answer there. And you will notice as you look at the graph that when x is 3.25, so I'm going over my scale, here's 1, 2, 3. 3.25 is somewhere in between 3 and 4. So somewhere in here, you go up to the graph, and this is the y value. And the y value, if you go across here, is 1, 2, 3. And that's how the graph works, okay? What about negative 4.6? Again, negatives can confuse people because it's hard for us to think kind of backwards with negatives. In the case of less than with negatives, the numbers get bigger, but they're bigger negatives, so that means that they're less. So in this case, for example, negative 4.6, an integer that is less than negative 4.6 is negative 10. Negative 10 is less than negative 4.6, but so is negative 9, negative 8, negative 100, negative 1,000,000. But which is the biggest one that is less than negative 4.6? It's negative 5. Okay, negative 5 is the biggest integer that is still less than negative 4.6. So be careful there. A lot of times people want to put negative 4 because they think of negative 4 as being, but it's actually negative 4 is bigger than negative 4.6. So it's negative 5, and again, if you go to your graph, negative 4.6 is somewhere between negative 4 and negative 5. So here's negative 4, negative 5, and somewhere in the middle. And if we go down to the graph, there's my y value, and if I go across here, my y value is negative 5. Okay, so what you see with the greatest integer function is that you have these steps, because any decimal that's between 0 and 1 is going to have an answer of 0. Like 0.7, the greatest integer that is smaller than 0.7 is 0. So all of these values have 0 as an answer. But once you get to 1, since it also says or equal to itself, if you get an actual integer, the greatest integer that is less than or equal to itself, in this case, it doesn't have to be less than because it can be equal to. And since this is an integer, then the answer would be 1. So you'll notice that when you get to 1 on the graph, it jumps up. There's no value here. There's an open dot. There's no value here. It jumps up to y equals 1. And then everything between 1 and 2 is 1. And then once you get to 2, it jumps up to 2. And that's kind of how it happens. So this is what the graph looks like. And so we want to show you how you can use this in an example. So here we have an example. It says an automotive repair center charges $50 for any part of the first hour of labor and $35 for any part of each additional hour. Draw a graph that represents this situation. And I will tell you right now that the easiest thing to do here is not asking us to come up with an equation, which would be a little more challenging. It's just asking us to figure out a couple of data points that we can actually graph. All right? A lot of times this is what piecewise functions are like. Even with cell phones, it's the same thing. Like when you call somebody, they'll charge you for the minutes, for example, in some plans. And if you're only talking on the phone for 2.5 minutes, they're going to charge you for the full-blown 3 minutes. And that's kind of what's happening here, is that even though they're only working on your car for 15 minutes, they're going to charge you $50 for any part of the first hour of labor. So what we've got here is I've kind of got a chart put together here for x values and y values, and I'm using integer intervals because I know that for any part from 0 to 1 hour, and notice that if it's 0, it's not equal to, and it's not equal to because if it's 0 hours, then hopefully if they haven't worked on your car, they're not going to charge you for 0 hours. But 0.1, they start charging you, right? 0. Anything, they'll start charging you. So for the first hour, you're only going to pay $50. Okay, but then it says for each additional hour, or any part of that hour, you're going to pay $35. So you already have to pay for the 50 plus the 35. So in that case, you're going to end up paying 85. So for this guy right here, we're going to have $85. All right, for the anywhere between the first and the second hour. Between the second and the third hour, on top of the 85, they're going to charge you another $35, and you're going to get 120. And then if you keep doing that, now you're going to get 155 for the next hour, and then for the final hour here, we're not going to get crazy. We're only going to go up to 5 hours. Hopefully, your car doesn't need to get fixed beyond that. If it does, I pity you. This doesn't even include parts. It's just the labor. But anywho, so this is what you're paying for the labor in these different increments. So now to graph it, because it wants us to draw a graph that represents a situation, it means that anywhere between 0 and 1, my y value is always going to be 50. So I'm just going to come right over here. And here's my my 0 and 1. These are by halves, right? So this is a half, 1, 1.5, 2, 2.5, 3. So there we go. Between 0 and 1, and since 0 is open, we are going to go to the 50 mark. So this is 20, 40, 60. So 50 is in the middle. So we're going to put an open dot there because they're not going to charge you, hopefully, for not working on your car. And then anywhere between then and 1 is going to be 50. So right here, we're going to go 50. Just make a horizontal line right across there. So for any portion between 0 and 1, you're going to get charged $50, including the one up to the 1 hour. Okay, after that, they're going to charge you 85. So between 1 and 2, we're going to jump up to 85. And here's 80, and 90 is in the middle, and 95 is in the middle of that. So you want to be really careful here. That's roughly 85, all the way to 2. Okay, that's supposed to be open. Hopefully that looks open. And then we're going to go to, for the second to the third hour, you're going to be 120. So now we're going to jump up over here. There's 120 between 2 and 3. And for that third hour, you're going to get charged 120. And it's starting to look like it's not quite lining up right, but hopefully you'll forgive me for that. And then we have for the fourth hour, 155. So this is 160, this is 150, 155 are about here. So we're going to go, oops, I lost my ink. There it is. All the way to the fourth hour, like that. And then lastly, for between the fourth and the fifth hour, it's going to be 190, which is right about here. Not quite 200 for that last hour, and that doesn't look open at all. So let's redraw that guy, make him a little bit more open. All the way to 5, and then you have that. And that's basically what this situation will look like on a graph. All right, so again, the easiest thing to do is to just kind of make yourself a t-table, and instead of doing like x is 1, 2, 3, 4, 5, is to use intervals between integers for the situation. So here we have a very similar scenario happening, and so in this case they're using p of x instead of y, but that's pretty much p of x is the same thing as y, and then of course you have your x. So it's a very similar situation, so hopefully you can draw that graph fairly quickly. All right, so then the last thing we want to talk about is absolute value functions. We've done absolute value in the past, and you might remember that with absolute value you always have to have two cases. So hopefully you haven't forgotten that. Sorry for the bell there. So I wanted to show you how we're used to seeing f of x equals absolute value of x, but behind the absolute value of x is an actual definition that is a piecewise function. It tells us that if x is greater than 0, so if x is a positive number, then we leave the x value the same. In other words, if we look at the absolute value of 5, since 5 is a positive number, it's greater than 0, then we know that the answer is just 5, which is x itself, okay? We know that at the absolute value of 0, which is neither positive or negative, it's just neutral, we know that the absolute value of 0, since if x equals 0, it's going to be 0. We know that already too. The one that gets kind of tricky is the absolute value of negative 5. We already know that the absolute value of negative 5 is positive 5, but how does that happen? According to the definition, you do negative x. So I put negative, and then I put x in here. Well, x is negative 5. And then negative was what makes that into a positive 5. So we all know that the answer is positive 5, but sometimes we don't remember that it's because it's negated. So that is the basis for why we have two cases when we solve for absolute value. So we can also graph this piecewise function with the three different pieces. We know that the easiest one to graph is the 0. How do we plot 0? It's very simple. When x equals 0, y is 0. So you just put a big fat dot right there. Okay? Then how do we plot x? Y equals x. Well, y equals x is a line. Y equals mx plus b. Y equals 1x plus 0, if you will. It's the same thing as y equals x. In that case, the y-intercept is 0. So we put our open dot, and I'm making it blue so you can see that. My open dot at the origin, because that's my y-intercept, but it says that x is greater than 0, not including 0. So we open that dot, and then the slope is 1, so you go up 1 over 1. And when you connect those points, you get the right-hand side of the absolute value function. Alrighty? But we also have the third part, which is the negative x. And again, negative x is the same thing as y equals negative x plus 0. So you still have the same y-intercept. So now we have another open dot. And that's good because that means that at 0, there's only one value there. There's only one function there. Even though there's technically 3, the blue, the green, and the red, only the red is the closed dot. The green is open, the blue is open, so only red has a value there, and that's what makes this still be a function. And then because the slope is negative 1, you're going to go down 1, right 1, and you connect those dots. But instead of graphing the right-hand side, this says to graph less than 0, which is the left-hand side. So you graph this guy, and that is how you get the V shape that we have known to call absolute value, the V shape, okay? So I just want to remind you that absolute value is a piecewise function, and therefore we need to be able to graph it as such. So our next and final example is graphing absolute value. And so here we go, and I just want to tell you that you don't have to graph it as a piecewise function per se, but it will make it somewhat easier. So what you want to do is remember that you have a positive case and a negative case for absolute value. And in the positive case, you basically leave everything alone. And so we're going to do that. If I leave it all alone, then the 2x just stays 2x. So in this case, I'm going to get y equals 2x minus 4. That's all I'm going to get, okay? But over here, in the negative case, remember if you recall from the negative case when solving equations, you're going to get that y equals negative 2x minus 4. You have to negate whatever is inside the absolute value bars. So now you have two separate functions. This was negative 2x minus 4, and this one's 2x minus 4. Now the only part that's left is where is the middle, okay? Because as you know, a V kind of comes together in the middle, right? So to figure out that part, you always take whatever is inside